let's begin with today's lecture and try to understand what a transistor is. The modern era of semiconductor electronics was ushered in by the invention of this transistor in the year 1948 at Bell Labs. It was driven by the need to design a device that could amplify signals. So telephony was the reason why people were spending time in figuring out how to increase the power in a signal when it's sent across a transmission line. How do we ensure that we can, or if we get a signal back at the other end, how are we able to amplify it to get our data out? So that was the reason why they were looking into it, and the first transistor was made for the same. The inventors of the transistor went ahead and received the Nobel Prize in Physics, and obviously, as all of you are aware, it has had an enormous impact in our lives. Almost anything we touch these days has some sort of transistors in them. So what we'll do is we'll begin to first understand what a transistor means, look at some very basic operation of the transistor, and then we'll look at a few use conditions. Basically, I'll try to introduce you to the two probably most important ways in which a transistor is used in electronic circuits. So transistors are what are known as active devices, right? So let's first understand what an active device is. So most electronic systems involve processing, right? So a system normally is made up of a few inputs, right? And then you make some decision and you drive certain outputs, right? So that is what typically we do when we design electronic systems. If we want to make a bigger system, what we do is we take similar such units and then put them one after the other, or what we know as cascade them, to create larger and larger systems, right? So you can think of a way by which you can put multiple of these, stack them one after the other, stack them in parallel to each other, depending on how you want to build your system, and go ahead and build a larger system. So when you're doing this process of cascading systems one after the other, typically what happens is you want to design a system that is able to drive more inputs than it receives, right? Especially as you start thinking of bigger and bigger systems, you want a certain output at one of your subsystems to drive decisions at multiple other outputs. So in this case, what you want is you want your basic system, your basic circuit, to drive an output that might be larger than an input, right? And this is where you want to think about what is that smallest device can do that, right? And that is where you see that the most elementary device in your electronic system must have gain. And what I mean by gain is that it should be able to supply more energy to its output corresponding to the inputs it gets, right? So if I measure the power in the output should be larger than the power in the input. If I look at the combined power at the output, suppose I have multiple outputs, then it should have way more power than my inputs. Only then would I be able to faithfully pass on my decisions through the system. Right? So that's where a transistor comes into play. So a transistor is an active device, usually with 3 or 4 terminals. So shown here, I've shown you one device which has 3 terminals, terminal 1, 2, and 3. Because it has gain, almost always we will see that it would be a nonlinear device. What do I mean when I say something is nonlinear is that the inputs and outputs are not necessarily linearly dependent on each other. That is, if I double my input voltage or double my input current, it is not necessary that my output voltage or current will double, right? And again, normally when you think of this system, a transistor has 3 terminals, full stop. When we use this transistor, we normally nominate one terminal as its input terminal, One terminal we nominate as its output terminal, and there is this third terminal or a control terminal, right? So typically when you think about these transistors, you want to electrically control how data or how signals pass through your system. Right? So the key feature of this elementary device that you are trying to implement is that it should have a control terminal that electrically controls what's happening between terminal 1 and 2, right? So in this case, in the most basic case, which we'll see for most of the transistors that are normally used in electronics, by controlling the current or the voltage at this terminal, you're able to control the resistance between terminals 1 and 2. Right? So by applying different voltages, for example, at terminal 3, I control what is the resistance I see between terminals 1 and 2. So if I make the resistance between 1 and 2 very high, then I'm going to have a device which is not able to send a lot of current through the output, right? So this device is known as a transresistance amplifier. What does that mean? That means that the resistance of this path, the path between 1 and 2, is controlled by this terminal. So it is able to transform the resistance between 1 and 2. So this transresistance amplifier was later coined down to a transistor. Now when you think about transistors again, you can think of them as either having a voltage control or a current control, right? Because normally when you think of electronics, we either talk about a voltage or we talk about a current. So here in this case, suppose I call terminal 3 my control terminal and 1 and 2 as my output terminals. I see that I'm able to control the current I1 or the voltage V12 by changing the voltage or the current on terminal 3. An example of a current control device is the bipolar junction transistor, or the BJT for short. A voltage control device is the field effect transistor, which is what we'll talk about in some of the classes later on. And then we'll talk about true primary applications, right? So let's think about this. Suppose I were plotting the current volt from 1 to 2 as a function of this voltage V12. So please remember, a transistor needn't be a linear device, right? So this I versus V12 is not a straight line. Right? It can be a straight line, can be approximated as a straight line under certain use conditions. We'll talk about that later. But as a general concept, I versus V can be any curve, right? And it's a causal system, so current increases as I apply some voltage. What you see is that the shape which the current follows as a function of voltage, that shape can change depending on the magnitude of the signal that I've applied on the control terminal. So essentially by playing around with the voltage or the current on terminal 3, I essentially change the characteristics of the device, right? Now, broadly speaking, as I mentioned, transistors are used for two applications. One is normally amplification, very simple signal amplification. So what does signal amplification mean? It means that you want to increase the power in an input signal. The other general application is known as switching, where you want to switch the state of the transistor from one stable state to another stable state. Now these two broad applications, sometimes for simplicity, break down into two different kinds of transistor design, if you will, an analog circuit design technique or a digital circuit design technique. But more on that later. Nature tends to attenuate signals, be it a sound signal or a light signal. As you walk away from the source of the sound or the source of the light, you begin to lose its amplitude. So in the case of the sound, as you walk away from the person who's generating a sound, you begin to hear it less and less, and eventually you're not able to hear what he or she is saying. Similarly, if there is a light source and you walk away from the light source, you start to see it gets dimmer and dimmer, and eventually you don't see the light source anymore. The same is true with electrical signals. So if you think about a very simple telephony system, what does a telephone do? A telephone converts your voice signal into an electrical signal. And as you send it across a medium, it is going to attenuate. That is, its amplitude is going to go down, which means that it becomes harder to extract the data as you receive the signal far away from where it is transmitted. So at the receiver end, this attenuated signal that you have has to be amplified again if you want to convert it back to a sound signal, or if you want to drive a diaphragm, or whatever the case may be, right? So there is a need at any, especially in most of signal processing, where you need to amplify signals to counter the effect that we normally have when we send signals on a medium. And that's one of the primary reasons why we look at devices which can amplify signals. The other application, if you think about it on a spectrum, there is one spectrum which deals with amplification of signals. The other way to think about transistors or use of transistors is in compute applications. So traditionally, if you think about your computers, cell phones, any digital device that you have, most of your data is stored in binaries. So it's either stored as a 0 or 1. So when you talk about digital logic, we talk about two states, a 0 and a 1. And what does that mean? Now, why are these 0 and 1? What do they mean? When we think about it in terms of circuit design, the 0 and 1 are nothing but two stable states of a transistor, right? So these can either mean that the transistor has zero current or infinite current. It can mean it has zero voltage or a large voltage, whatever the case might be, right? So you're coding the 0 and 1, which are what you use to represent information digitally, into two stable states. So the importance is stable, because suppose I'm storing something in my memory, in my computer, I don't want to change it over time, right? So I want to make sure that suppose I'm storing a 0, I want to make sure that my 0 stays a 0 till I decide to change it to a 1. So you want the state where you're coding the transistor to remain in that state until I apply a stimulus for it to change. So when you think about switching applications, you're thinking about a transistor which can exist in two stable states, and you have a way of switching between these two states, right? And again, as we looked at in the previous case, you tend to think about a path, a data path, a computation path, which is going to have multiple of these switches aligned one after the other as you process data through your data path, right? And so there you have a case where your transistors or your devices are continuously switching states as and when new information comes into the system. The other thing, as I mentioned, is that this transistor has to be stable, right, in two states. The other important thing is these two states have to be as distinct as possible from each other. Right? For example, suppose I code the two states as 0 volts and half a volt, as opposed to 0 volts and 3 volts, right? I would prefer the 0 volts and 3 volts. Why is that? Because 0 and 0.5, I have a very small separation between the two voltages. So in case there is some extraneous voltage that gets coupled onto my circuit, it is possible that what I initially started off as a 0 can quickly move up to 0.5, right? Due to some static charge or something, or vice versa, my 0.5 can drop down to 0. Suppose I have my two states coded up as 0 volts and 3 volts, then I can keep them as distinct as possible from each other. So there is that requirement also from the transistor, that you want to be stable in two states, and you want those two states to be as distinct from each other as possible. Now let's look at this transistor in a circuit. So a simple way of thinking about a transistor, again let's talk about the three terminals of the transistor. I have a 1, a 2 and a 3, right? And so I have 3 is my control terminal, and the current into my control terminal, I'm taking an example of a current control device. So the current flowing in terminal 3 controls what's happening between 1 and 2, right? So if I assume this is a current control transistor, by varying the value of IT, right, by varying this current that's flowing into this terminal, I can change how my output current, so this current, if I look at this current ID, I can change how my ID VD characteristics look like based on the value of IT, right? So as my IT changes from 0 here all the way to 0.2 milliamps, I can get an increase in ID from close to around 1 or 2 milliamps all the way to 20 milliamps, right? So 2 points I want you to note. One is that you're able to change the value of ID by playing around with the value of IT. But the second important thing that you want to note is also is that the variation that you get in ID for a given range of IT is much larger, which means that for a 0.2 milliamp change in IT, I'm able to get a 20 milliamp change in ID, right? So suppose I now think about a case that I have a small AC signal, a sinusoidal signal connected to IT, connected to the control terminal. I expect my ID to show a signal which is going to have an amplification of roughly 10. What does that mean? I said 10 because when IT goes to 0.2, I'm getting roughly 20 milliamp current. So which means that for small changes in ID, I'm going to get a large change in ID. This IT goes small, ID goes large, and that is the amplification. So if I think about a case where I have an incoming signal coded in as a current, as an IT, then my output can be taken from ID, and that's going to have a larger variation in amplitude, which means that I've amplified the signal. Now the same thing can be thought of also from the point of view of switching. Suppose I'm able to turn on and off a switch that is connected as input, where when the switch is turned off, I have 0 current flowing into the control terminal, and when the switch is turned on, I have 0.2 milliamps current flowing into the terminal. What you see is that ID also shows 2 stable states. Your ID can either be close to 1 milliamp or 2 milliamps, or can go as high as 15 milliamps, right? So as long as I'm able to switch between my IT levels of 0 and 0.2, I will be able to stay at these 2 stable states, and I can code them as a 0 or a 1, right? How we code them up, etc. will come in subsequent lectures. So I can think about these 2 as 2 stable states in which the transistor can exist, right? And that's where I can use this transistor as a switch. And so I can cascade similar transistors to design a logic circuit. So to summarize, key points to keep in mind when you think about the transistor is that the transistor, or the basic elementary device when you think about circuits, is the ability of the transistor to provide higher power at the output. That is the key defining characteristic of a transistor, the key defining characteristic which we will use to make use of the transistor in applications. And as I pointed out, applications are generally or broadly classified into 2. You have the application of amplification or the application of switching. And again, we will look at exceptions to all this subsequently. Normally when you think about a transistor, it has 3 or 4 terminals. Normally one terminal is the control terminal, and that control terminal determines how the electrical characteristics of the other 2 terminals look like in the device. So electrically you are able to control how 2 other terminals on the device look like, and that gives a key for you to cascade such systems so that one output controls the input of the next stage and so on and so forth. So you start to create larger systems where information flows from one end of the system to the other, and you're able to create logical systems as we go forward.